Hello, in this webinar we are going to talk about the mathematical evolution of human behaviors. Human behavior modeling has been the focus of many researchers over the last years. It is spreading enormously over a wide variety of applications such as video games, social studies, marketing, and so on. Different techniques have been used to address intelligent agents in human-like behavior. Most previous trials for modeling human behaviors targeted predicting the future actions that a person or a group of persons may take. This includes predicting the next steps of a video game player, estimating the movements of a pedestrian on a street, anticipating the future choices of a user based on his past choices, and so on. This webinar talks about the artificial imitation of actual human behaviors such as wisdom, rashness, carelessness, and so on. Once an intelligent agent imitates a certain human behavior, it can autonomously take the same actions that a human user with the same behavior is expected to take. That is, a wise intelligent agent is expected to behave like a wise person when encountering the same situation. For an intelligent agent to imitate a human behavior, it must take the same actions a human may take when encountering a certain situation. Thus, a human exemplar must exist. Imitating that exemplar follows one of two techniques, direct and indirect behavior imitation. In direct behavior imitation, a controller is trained to output the same actions a human took when he faced the same situation. This means that the performance of the controller depends on the performance of the human exemplar. On the other hand, an indirect behavior imitation controller is allowed to generate actions freely, that is, unguided by a human exemplar. Afterwards, the controller is evaluated by comparing its actions with those of the human exemplar. This freedom in generating actions gives the indirect techniques more generalization over the direct ones. The main difference between direct and indirect techniques is that direct techniques imitate human actions, while indirect techniques imitate human behaviors. The novelty of the method introduced in this webinar is that it gives the intelligent agent more freedom and more generalization even over the indirect techniques. It extends the freedom of the indirect techniques by allowing the intelligent agent to evaluate itself without any human exemplar. That is, the intelligent agent is just provided with a fitness function and left in the environment. It examines the environment, evaluates different human-like behaviors, and selects the fittest one of them for that environment. First, let us talk about the society of mind theory, which is the basis of this work. Next, we will talk about the learning intelligent agents and how to utilize them in the society of mind theory. Next, we will talk about the Robocode game, which is used as a benchmark for this work. Next, we will build our human imitating system and test it on Robocode game. Finally, we will try to predict how our system can be used in our daily life. Let's start by talking about the Society of Mind theory, which is introduced by Marvin Minsky in 1970s. It is published comprehensively in 1988. It envisions the human brain as a society of agents. Every agent on its own is not intelligent, but all agents should cooperate together to solve a problem. Let's have an example. We have a number of blocks and we want to build a tower. Assume that we have a builder intelligent agent which has the responsibility of building such tower. This task seems too complicated for a single agent to accomplish alone. First, we need to find the proper location for constructing the tower. If we choose the wrong location, the tower will fall down. So, let's assign this task to an agent and call it Begin. It is responsible for selecting the proper location for constructing the tower. However, selecting the proper location is not sufficient for building a good tower. It will fall down if we didn't stack blocks properly. So we need another agent to hold the responsibility of stacking blocks properly. However, this is not sufficient for building a good tower, because growing the tower too high will make it very subject to fall down. So let us have another intelligent agent and let us call it Ant, which has the responsibility of determining the proper height of the tower so that it doesn't fall down. The same way, we can break the begin task into find for finding the block from the ground and getting that block and putting that block on the stack. We can repeat the same principle and have another sub-society of agents. Now let us examine what is inside every agent. Every agent is a learning intelligent agent. As we see, an intelligent agent interacts with the environment. It reads perceptions from the environment through its sensors and keeps inside its brain the environment state. It has a performance element which determines which actions should be taken on the environment to satisfy the agent. Then these actions are sent to the actuators of the agent to be taken on the environment. There is a critique element which is responsible for evaluating the performance of the agent based on a fitness measure. It sends a feedback to a learning element which is responsible for modifying the performance element so that the agent performs better in the future. Now let us examine the benchmark that we used for evaluating our work. It is the Robocode game. Two robots battle in an arena. Each one tries to shoot bullets at the other to destroy it. Each robot consists of the following: a radar for detecting its enemies, a gun for shooting at them, and body for moving and for holding the gun and the radar. Now our task is to build a human imitating system to be implanted inside a Robocode tank. This means that the tank should behave like a human player. Let's modify the traditional structure of an agent to be a society of agents. Let's first replace this word agent by agent system or agent society. The strategy we will follow is that our robot will observe the motion of the target and try to build a model of this motion. This model can then be used for predicting the future location or the future path of the target so that we could find the proper location and time for hitting it. First, let's say that the environment is the enemy robot and the sensors we have is the radar. Then the environment state is the position of the enemy, and we have only one actuator, which is the gun. The performance element will be replaced by 3 agents. A modeling agent, which is responsible for building models of the motion of the target. Then these models will be used by an estimation agent, which is responsible for predicting where and when to hit the target. This information is sent then to the shooting agent, which takes the final actions and sends them to the gun. Let's replace the learning element with evolver agents that are responsible for adapting the other agents. Finally, the critique function will be implanted in parent agents. Now let us rearrange the system in the form of a society. For the evolver agents, we will be using 2 methods, the Neldermead method and genetic algorithms. They will be responsible for adapting the modeling agent. And let's make the shooting agent the parent of the modeling agent. It is responsible for evaluating its performance through the fitness measure and sending feedback to its evolvers, the Neldermead and the genetic algorithm, and triggering these evolvers. Now we have the main structure of the agent system. Let's call it the Human Imitating Cognitive Modeling Agent, HICMA. Now let's see the structure of every agent. Every agent has an identifier and a set of evolvable parameters. Evolvable means that these parameters can be updated or adapted online. In turn, every parameter has an initial value, evolver type, and a fitness measure for evaluating the performance of the agent by this value of the parameter. Now, let's examine the agents of HICMA one by one. Let's start by the modeling agent. The modeling agent, as we mentioned before, is responsible for building a model of the motion path of the Robocode enemy tank. This is done by taking samples of the motion of the target in the arena, so that we could use this model in the future to predict the future location of the target. Once we build a model of the motion of the target, we can predict the location of the target at any time. But what is the form of the function to be used as a model? Here we have 4 main functions: quadratic, linear, exponential, and cosine. We select two of them, combine them together, and assume that the model of the motion of the target will follow this form. After selecting a form of the model, we have some unknown parameters, like A1, B1, C1, A2, and B2. Now our task is to find the values of these parameters. Now let us use this function as a loss function or an objective function of an optimization process. First, we will use the covariance matrix adaptation evaluation strategy along with the samples of the location of the target as it moves in the arena. The output of the CMAES will be a near optimal solution of the parameters. To fine-tune these parameters, we will pass them to Nelder-Mead method, and the output will be fine-tuned solution. Let us call the combination of the CMAES and Nelder-Mead the hybrid method, but we select the combination of the basic mathematical functions. In fact, this is done by genetic algorithm. So, let us examine the genetic algorithm evolver. Assume that a chromosome consisting of 3 genes holds 3 numbers. Each represents an index of a function of the mathematical basic functions. Now let's examine the mutation process. First, we will initialize a temporal lexicon, let us call it temp, with the set of all function indices. And let's also initialize an empty new chromosome. Next, we will define a mutation constant, PMC, within the interval 0 and 1. Let's generate a real number within the interval 0 and 1. If this number is found less than or equal to PMC, we will make a mutation. Otherwise, we will copy the old gene from the old chromosome as it is. Assume that we will mutate the first gene. This is done by copying a random gene from the lexicon and examining whether it exists in the new gene. Certainly it doesn't, because this is the first one. Let us move to the next gene. Assume that we will copy it as it is from the old chromosome. Here a conflict happened. We cannot have a repeated gene because it has no meaning. We will not gain any benefit from adding a function to itself. So we will remove this repeated gene and copy a random one from the temporary lexicon. Let's proceed the same way until all genes are filled. The fatness is the bullet miss rate, which equals to the number of bullets that hit the target to the total number of bullets. The selection method is the roulette wheel, and we have one elite every generation and mutation as we have just explained. Now let's proceed to the estimation agent. The function of the estimation agent is to estimate the proper location and time to hit the target. After we had a model of the motion of the target, and knowing the location and the bullet speed of our robot, we can detect the current location of the target and combine all of this information to build such a function like this. On the left hand side is the motion of the bullet, and on the right hand side is the motion of the target. When the bullet and the target meet at the same location at the same time, this means that the target was hit by the bullet. There is only one unknown in this equation, which is the time. Solving this equation gives us the proper time for hitting the target. We can solve this equation by using the hybrid method we mentioned before, which consists of the combination of the covariance matrix adaptation along with the Nelder-Mead method. After finding the proper time for hitting the target, we can use the models we got by the modeling agent to find the estimated location at that time. The output of the estimation agent is the proper position and time to hit the target. This information is then sent to the shooting agent, which acts as an interface between the estimation agent and the gun. It receives the estimation, the time and the position from the estimation agent and sends a command to the gun in the form of at time t, turn to angle theta and shoot a bullet. The shooting agent, as a parent of the modeling agent, has another function, which is providing its evolvers with fitness feedback and triggering these evolvers. The final agent in the society is the Nelder-Mead evolver. Please don't confuse the Nelder-Mead evolver with the Nelder-Mead method as used in the modeling agent as a part of the hybrid optimization technique. They are the same algorithm but used differently. As we mentioned before, every agent has a number of parameters. We don't know the optimum value of every parameter, And this is the task of the null-limit evolver. It tries to find the optimum value of every parameter. For example, let's examine 4 parameters of the modeling agent: the initial guess, the step size, the tolerance, the sample size. Every parameter of these has a different fitness measure. For example, the fitness measure of the initial guess is the iteration count. The less iterations the algorithm takes to find the optimal solution, the better it is. Now let's examine how the null-limit evolver works. First, we have an old value of the parameter and a fitness measure defined for this parameter. The parent, which is in our case the shooting agent, evaluates the value of this parameter using the fitness measure and provides fitness feedback to the null-limit evolver. The null-limit evolver receives this fitness feedback along with the old parameter value and suggests a new value of that parameter. This new value replaces the old one and tested on the next Rabocode round. The process is repeated until we get a satisfying result. Now the theory behind the system is explained. Let us see whether this works or not. We have 2 types of experiments. The first measures human similarity, and the second observes the evolution of the system. Human similarity has 2 experiment types: human behavior imitation and human performance similarity. Let's start by human behavior imitation. Now, this is the time to see whether our system will behave like a human or not. We have 2 Rabocode opponents: the shadow opponent, which is very tricky, and the walls opponent, which is very predictable. We allowed our agent to play against every one of them and observe its behavior. As we see, the shadow robot is very tricky. It makes tricks to dodge bullets. It is not easy to hit it. The task of our agent is not going to be easy. On the other hand, walls is very predictable. It is very easy to hit it because it moves along the walls of the arena. We selected those 2 opponents because they represent the extremes of the difficulty level of Rabocode opponents. For every opponent we have some statistics. The hit percentage, which is the number of bullets that hits the target to the total number of bullets, and the average shooting interval, which is the round time in turns to the total number of bullets. And we also have the standard deviation of the average shooting interval. For the objective function that is used in the modeling agent, we change the function pair in every case. For example, let's examine the function pair 1 and 2, which are the linear function and the exponential function. We notice that the hit percentage is very high and the shooting interval is small. This means that it shoots quickly at the target. We also notice that every function pair resembles a certain human behavior. Let's compare the function pair 0 and 2, which represents the careless behavior, with the function pair 1 and 2, which represents the tricky behavior. Now focus and see how careless is our agent when using the function pair 0 and 2. It doesn't seem to be in a battle. It doesn't care its opponent. It doesn't shoot bullets frequently, and even the bullets it shot didn't hit the target. Now let's examine the tricky behavior, and please focus to see how tricky is it. Even against the very tricky shadow behavior, it can't trick it. It tries to surround it by its bullets. Through our experiments, we notice that tricky behavior is the only one that got beat the shadow behavior, which is also tricky. This is because diamond cut diamond. We repeated the same experiment against the wall opponent. Now let's examine another function pair, which is 0 and 1, which represents the wise behavior. We notice that it has the highest hit percentage and its average shooting interval is moderate. This means that it doesn't waste its power on shooting straight bullets. Also, the standard deviation of the average of shooting interval is not very high. This means that it shoots bullets rather regularly. Here we have another parameter, which is the round time. We didn't have this parameter in the previous experiment because not all behaviors could beat the very tricky shadow behavior. We noticed that the wise behavior has the shortest round time. Now let us compare other two behaviors. The 2-3 function pair, which represents the unwise behavior, and 0 and 1, which represents the wise behavior. Now let's compare the two behaviors and see how the first one is unwise. It shoots astray bullets, a lot of astray bullets. Almost none of them hit the target. It wastes its power on these astray bullets, and finally it loses its power and loses the game. Now let's see the wise behavior. It doesn't shoot until it becomes certain that its bullet is very likely to hit the target. Keep in mind that all of these behaviors use the same code, just one parameter, which is the function pair, is changed. For measuring the similarity of human behavior, we allow 10 human players to play against the two opponents, the Shadow and Walls. And we also brought 3 hand-coded robots, TrustGT, Great Safford, and Wallaby, along with our agent, which is Higma. Every one of these players played 10 rounds against Shadow and Walls, and we compared the average score. These pink bars represent the deviation from the average score of the human players. In the case of Walls, we noticed that the closest score is Higma's score, our agent's score. However, in the case of Shadow, the closest one is Wallaby, but our agent could get a score that is close to the average of the human players. On average, if we tabulate these results, we will find that the closest result is the result of our agent. It has the closest performance to the human players. Now let us come to the final experiment, which is the evolution experiment. Let us compare the evolution of our agent with the evolution of the human players. This experiment measures how our agent learns similar to human players. In case of Walls, we recorded the hit rate and plotted them on this graph. We repeated the same experiment with Shadow. We noticed that there is no important improvement in performance. When we repeated the same experiment with human players, we got similar curves. We noticed that both Higma and the human players got similar improvement in performance, in case of Walls and also in case of Shadow. Having systems that behave humanly can enhance ubiquitous computing and Internet of Things. Imagine that devices that surround us behave humanly for serving their human user. This would be very great. Ubiquitous robots. Imagine that our servants became robots. They will understand our behaviors. Also, in this webinar, we introduced an easy way for representing human personality. Just by changing some parameters of a model, we can change the personality of the system. In the future, we can have driverless cars that behave humanly. Imitating human behaviors gives the intelligent agent an advantage over imitating the human actions, because imitating human behaviors makes the intelligent agent able to generate an unlimited number of actions, and also encountering unknown situations and new situations. This may be useful in discovering space and unknown planets. Making intelligent agents more human may contribute to education, because the children will love human machines more than the traditional machines. The final words that I want to say is thank you.